Let's explore the surface thermodynamics of water in depth. So let's break the surface tension into different thermodynamic components. We can do this pretty easily if we write out our expression for the differential of the Gibbs function. And using this convention, we can see if we just take the derivative of both sides with respect to A, that the partial of the Gibbs function with respect to area is equal to the surface tension. And this is, of course, at constant temperature. So we can see that surface tension is really just the Gibbs energy per area of that interface. And so we can call that G sigma. So surface tension and G sigma are really the same thing. So we have G sigma, but how do we break that Gibbs energy for the surface into an enthalpy part and to an entropy part? Well, in the previous podcast, we saw that using a Maxwell relation, we can get the entropy from the derivative of the surface tension with respect to temperature. So if we can just get that data somehow, either by measuring it or looking it up, we can calculate S sigma. What about H sigma? Well, we know that the Gibbs energy is just equal to the enthalpy minus temperature times the entropy, and we can write this for any system, including for the surface. So this means that if we have the surface tension, we already have G sigma. If we have how the surface tension varies with temperature, we have S sigma, which means we can solve for H sigma. And that's assuming that these two parts are approximately constant over a relatively small temperature range. So we can write that the surface enthalpy is just going to be the surface Gibbs energy plus the temperature times the surface entropy. All right, so now that we have that, let's look up what these numbers are for water. At the National Institutes of Standards and Technology's webbook. So just Google NIST webbook and you'll find this pretty easily. Put the name of the compound, so we just want to look at water. And we want fluid properties. And we'll use units of kelvins for temperature, bars for pressure. Everything else in here looks good. Surface tension, we'll use dyne per centimeter, which is same as a millinewton per meter or a millijoule per meter squared. So for surface tension, we have to go along the saturation curve. And then we're going to go ahead and get some data. And let's explore the properties of water near room temperature. So we'll go from maybe 275 kelvins up to 325 kelvins. And we'll just go by 1 degree steps. Press the data. And in a moment, it will give us all the data we need in terms of a graph. And so we could graph, for instance, on the temperature on the x-axis and surface tension on the y-axis. And we can see, it looks like there's roughly a linear dependence for our data. So if we're going to manipulate this data, we want to be able to put it in Excel or something, or MATLAB. So right-click on the data, save it, and we'll just call it water data. When you try to open up one of these delimited files in Excel, it will figure out how it's delimited, so you can pretty much go right to the end and it will import correctly. And really all we care about was the temperature and surface tension columns. So let's go ahead and delete all this. Okay, so we have the surface tension varies from just above the melting point of water from 75 millinewtons per meter and up to 325 kelvins to 67. So we're going to graph this. We graph it, we can get the slope, and from that we can get the surface entropy. When we're done graphing this, we can see that it's approximately linear. There's a little bit of curvature, but we'll still take the slope from this. And it's a negative 0.155 millinewtons per meter per Kelvin. Okay, so we actually have the value of this slope because we graph surface tension as a function of temperature. So let's go ahead and do that calculation down here. We said the surface entropy is the negative of the change in surface tension with temperature. And so that number was negative 0.155 millinewtons per meter per Kelvin. So we can say this is going to be a positive 0.155 millinewtons per meter per Kelvin. And that is our surface entropy. We can use that to calculate our surface enthalpy. We know that the Gibbs surface energy is just the same as the surface tension. So at room temperature, we saw that was 72 millinewtons per meter. And if we're working at room temperature, it's 298 kelvins. And then we saw that the surface entropy was a positive 0.155 millinewtons per meter per Kelvin. So the surface enthalpy is going to be 118 millinewtons per meter. And so let's compare that to the surface Gibbs energy of 72 millinewtons per meter. We can see that there is a very high energy cost to making a water surface, but some of that is mitigated by having a positive surface entropy, and so that results in the Gibbs energy of the surface being somewhat lower than the Gibbs enthalpy.